Your production database is humming along, thousands of queries per second. Then the EC2 instance terminates. But when you launch a new one, the data is still there. How? The disk wasn't inside the server. That disk is actually a network storage volume, living on dedicated storage servers, replicated for durability, and connected over a custom protocol that delivers sub-millisecond latency. This is Amazon EBS. How EBS actually works under the hood. The complete masterclass on the storage engine behind every EC2 instance. Here is our roadmap. We will start with the mental model of what EBS is, then dive into its architecture and the complete I/O path. We will compare all volume types, explore how snapshots work, understand encryption, meet Physalia the control plane, and finish with performance tuning. Let's begin. EBS stands for Elastic Block Store. Think of it as a virtual hard drive that plugs into your EC2 instance over the network. Your OS sees it as a regular NVMe device. You format it with extension 4 or XFS and use it like any local disk. But unlike a physical hard drive, EBS volumes persist independently of the instance. Stop the instance, terminate it, the volume survives. Your data is replicated within the availability zone, and volumes can be detached from one instance and attached to another in seconds. It's network storage that behaves like local storage. The scale is staggering. EBS processes over 140 trillion operations daily. A single instance today gets more IOPS than an entire availability zone could deliver in 2008. Think of EBS like a safe deposit box at a bank. Your valuables live at the bank. Even if your house burns down, the contents remain safe. The network is the road between your house and the bank. Let's look at the architecture. An EBS volume lives on a cluster of storage servers within a single availability zone. Your EC2 instance connects to these storage servers over the network, but not ordinary TCP. AWS built a custom protocol called SRD, Scalable Reliable Datagram. The magic starts at the Nitro card. Every modern EC2 instance has a dedicated Nitro card for EBS. This card handles all block storage I/O, converting NVMe commands from your OS into network requests to the storage servers. It also handles encryption in hardware, with zero CPU overhead on your instance. On the storage side, your volumes data is split across multiple storage servers. Each write is replicated to at least 2 storage nodes before EBS acknowledges it. This replication is what gives EBS its durability. 99.999% for IO2, meaning you might lose one volume in 100,000 per year. SRD is what makes this feel local. Unlike TCP, which forces strict in-order delivery, SRD sends packets across up to 64 parallel network paths simultaneously. It handles congestion control and retransmission in hardware on the Nitro card. The result is 85% lower tail latency compared to TCP and throughput up to 25 gigabits per second. Let's trace a single write through the entire stack. Your application calls write. The OS kernel packages this into an NVMe command and places it on the NVMe submission queue. The Nitro card picks it up, encrypts the data block using the volume's ES-256 data key, and fragments the write into SRD packets. The Nitro card sends these packets to the primary storage server. The primary server writes the data to its local SSD and simultaneously forwards the write to the replica server. Both servers acknowledge. Only when both acknowledgements arrive does the Nitro card post a completion on the NVMe completion queue. Your application sees the write as complete. The entire journey, application to kernel to Nitro card to storage server to replica and back, takes under 1 millisecond for IO2 block express volumes. For GP3, it averages around 2 to 4 milliseconds. Reads are simpler. The Nitro card sends the read request to the storage server that holds the data. The server reads from its SSD and sends the data back over SRD. The Nitro card decrypts the block and places it on the NVMe completion queue. No replica involvement on reads, just one hop. This is why reads are typically faster than writes. EBS offers 5 volume types, each designed for different workloads. They split into 2 categories: SSD-backed for random I/O and transactional databases, and HDD-backed for sequential throughput workloads like streaming analytics and log processing. GP3 is the recommended default. It includes 3,000 baseline IOPS and 125 megabytes per second of throughput regardless of volume size. The key innovation is independent scaling. You provision IOPS and throughput separately without buying extra storage. It's 20% cheaper than the older GP2. For mission-critical databases, IO2 Block Express is the top tier. It delivers up to 256,000 IOPS and 4 gigabytes per second throughput with sub-millisecond latency. Its durability is 5 nines, 99.999%. It also supports multi-attach, letting multiple instances share one volume. For throughput-heavy sequential workloads, SD1 delivers up to 500 megabytes per second, perfect for Kafka, Hadoop, or streaming logs. SC1 is the cheapest option at 1.5 cents per gig, ideal for cold data you rarely access. EBS snapshots are point-in-time backups stored in Amazon S3. But here's the clever part. They are incremental. The first snapshot copies all blocks from the volume. Every snapshot after that copies only the blocks that changed since the last snapshot. EBS tracks changes at the block level using 512 kilobyte blocks. When you create snapshot B, EBS identifies which blocks changed since snapshot A. Only those changed blocks are compressed and uploaded to S3. Snapshot B still references the unchanged blocks from snapshot A, no duplication. Restoring is equally smart. When you create a volume from a snapshot, EBS lazily hydrates the data. The volume is immediately available. Blocks are fetched from S3 on first access. You can also copy snapshots across regions for disaster recovery. You only pay for the changed blocks, not the full volume size. A 1 terabyte volume where only 10 gigabytes changed costs you 10 gigabytes of snapshot storage. The EBS Direct APIs let you compare blocks between snapshots programmatically. EBS Encryption uses AES 256, and the key management involves a fascinating multi-layer design. When you create an encrypted volume, AWS KMS generates a data key. This data key is encrypted by your KMS master key and stored as volume metadata. When you attach the volume, the encrypted data key is sent to KMS for decryption. But KMS doesn't hand back the raw key. It re-encrypts it using the Nitro host's unique public key. The key then travels to the Nitro card double encrypted, once by TLS on the wire and once by the host's asymmetric encryption. Only the specific Nitro card's private key can decrypt the data key. The hypervisor never sees the plaintext key. Encryption and decryption happen in dedicated hardware on the Nitro card with zero performance penalty. This is why AWS recommends encrypting every EBS volume by default. The EBS control plane has a fascinating history. Early on, a single control plane failure caused a cascading brownout across all EBS volumes. AWS needed something that could not fail at scale. The answer was Physalia, millions of tiny databases. Each Physalia cell is an independent, 7-way replicated Paxos instance. Every EBS volume gets its own cell. If a cell fails, only that one volume is affected, not the entire service. Physalia places replicas based on data center topology so that no two share too much infrastructure. The result is a control plane with a blast radius of exactly one volume. Physalia stores the configuration for each volume, which storage servers hold its data, replication state, and encryption metadata. It's the glue that makes everything else work. Performance tuning starts with understanding 3 metrics: IOPS, operations per second, throughput, megabytes per second, and latency, time per operation. These are related. IOPS times I/O size equals throughput. Latency increases when queues build up. This is queuing theory in action. Every EC2 instance has an EBS bandwidth limit. An M5.0 large gets up to 3,500 IOPS. An R6i.8 large gets 40,000. If your volume supports 64,000 IOPS, but your instance only supports 10,000, the instance is your bottleneck. Always match volume performance to instance capabilities. CloudWatch metrics are essential. Watch volume read ops, volume write ops, volume queue length, and volume throughput percentage. If queue length exceeds 1, your volume is saturated. If throughput percentage hits 100, you've maxed out the instance or volume limit. Let's build the mental model. Your application writes to what looks like a local NVMe disk. The Nitro card encrypts the data and sends it over SRD to storage servers. The data is replicated to multiple nodes. Physalia manages the configuration. Snapshots capture incremental backups to S3, and the right volume type matches the right workload. EBS evolved from shared hard drives in 2008 to a massive distributed SSD fleet processing over 140 trillion operations daily. The Nitro System, SRD protocol, and Physalia control plane make network storage feel indistinguishable from local disks. Understanding these internals helps you choose the right volume type, set correct IOPS limits, and diagnose performance issues. EBS is not just a disk. It's a distributed storage system engineered at an unprecedented